In example 4 from section 10.2, we are asked to find the critical numbers and where the function is increasing or decreasing, find where the function is concave up or concave down, and any inflection points. And then we are asked to sketch the graph of the function. If we need to find critical numbers and increasing or decreasing, then we need the first derivative. So the first derivative is 4x to the third minus 36x squared. Set this equal to 0, and notice that 4 and x both factor out of each term. If we do that, we will have x squared minus 9 left inside, and that factors into x minus 3 times x plus 3. So our critical values, or critical numbers, are x equals 0, x equals 3, x equals negative 3. So we're going to set those three numbers on the number line. And then we are going to test numbers in the first derivative. I'm going to test negative 4. I am using the factored version of the derivative, and putting negative 4 into that factored version will give us negative 16 times negative 7 times negative 1. 3 negative signs gives you a negative answer, so all of this area is negative. Between negative 3 and 0, let's test negative 1. Putting that in the factored form, we'll get negative 4 times negative 4 times 2. And 2 negative signs equals positive. So between negative 3 and 0 is positive. Between 0 and 3, testing 1, we would have 4 times negative 2 times 4. 1 negative sign gives you a negative. And then on the right side of 3, testing 4, we would have 16 times 1 times 7. All those are positive, so we get positive. What we know now is that we are increasing on the interval from negative 3 to 0, and again from 3 to infinity. We are decreasing from negative infinity to negative 3, and again from 0 to 3. And as far as maxes and mins, at negative 3, we are decreasing before it and increasing after it. So we have a relative min at negative 3, negative 76. At 0, we are increasing before, decreasing after. So we have a relative max at 0, 5. At 3, we are decreasing before, increasing after. So we have another min at positive 3, and putting the back into the original, you get negative 76. Now we need to find concavity. To do that, we need the second derivative. The second derivative will be 12x squared minus 36. Set that equal to 0, and notice that 12 factors out. That would leave us x squared minus 3 inside. The 12 gives us no critical numbers because there's no variable there. So all we need to look at is the x squared minus 3 equals 0. Add 3 to both sides, you get x squared equals 3. Take the square root of both sides, you get plus or minus the square root of 3. So our two possible inflection point values are plus and minus the square root of 3. So we need to put those on the number line. And this is where our second derivative equaled 0. Now, just so you know, the square root of 3 is about 1.7. So when we decide on our testing, we have to use that number to help us figure out what to do. I'm going to test -2 in the left section. Putting it into the factored version, we will have 12 times -2 squared is 4 minus 3 is 1, which is positive. So the left side of negative square root of 3 is positive. Between the two numbers, let's test 0. We would have 12 times -3, which is a negative number. And then on the right side, let's test +2. We would have 12 times 4 minus 3, which is 1. That's going to be positive. So the right side of radical 3 is positive. We now know that we are concave up from -infinity to negative square root of 3, and again from square root of 3 to infinity. We are concave down between negative square root of 3 and positive square root of 3. Because we did change sign on each side of both of these radicals, they are inflection points. So we have inflection points at negative square root of 3. Putting that into the original, you get -40. And at positive square root of 3, which in the original also gives you -40. On this screen, I have rewritten the summary of all the information that we found previously so that we would have it all in one place and be able to see it while we are doing our graph. One of the things that you need to recognize is that the relative max and relative min are points on the graph, and inflection points are points on the graph as well. So looking at those points, notice that we have y values of -76 and -40. So I need to change my scale on here, and I'm going to count by tens on my y-axis. The x-axis I'm going to leave as ones. Now, relative max occurs at 0, 5. We have a relative min at -3, -76. You're going to have to kind of estimate where that is. And again at +3, -76. We have inflection points at negative square root of 3. Now remember that the square root of 3 is 1.7. So -1.7, -40, and +1.7, -40. Now use the increasing and decreasing to help you draw the graph. We are decreasing Look for the negative infinity. We are decreasing from negative infinity to negative 3. So all the way to that first point, we are decreasing. Then we increase from negative 3 to 0. We decrease from 0 to 3, and then we increase again from 3 to infinity. I always use the increasing and decreasing on my sketching and then check my concavity. We're supposed to be concave up from negative infinity to negative 1.7. If you look at this from negative infinity to negative 1.7, aren't we cupping upward? And then from negative 1.7 to positive 1.7, we're supposed to be cupping downward. And that's what happens. And then we cup upward again from positive 1.7 to infinity. So you can see that our concavity fits what we said was happening with increasing and decreasing as well. So this is the sketch of the graph of the function. On example B, our function is f of x equals x to the fourth minus 2x cubed. And we want to be able to sketch a graph of this. So we start by finding the first derivative to find increasing and decreasing. Our first derivative will be 4x cubed minus 6x squared. Set that equal to 0. And notice that you can factor out a 2 and an x squared. If you do this, what will be left inside will be 2x minus 3. So our critical numbers are x equals 0 from the 2x squared and x equals 3/2 from the quantity. Set those on a number line. And then do your testing in the first derivative. Left of 0, I'm going to test negative 1. If I put negative 1 into the factored version of the derivative, I will get 2, because negative 1 squared is 1, 2 times negative 2 minus 3, which is 2 times negative 5, which is negative. So the items to the left of 0 will be negative. Now test between 0 and 3/2, which is 1.5. The easiest thing to do would be 1. Putting 1 into our derivative will give us 2 times 2 minus 3, which is 2 times negative 1, which is still negative. So the items between 0 and 3/2 are also negative. To the right of 3/2, let's test 2. Putting 2 out front will give us 2 times 4, which is 8, times 4 minus 3. 8 times 1 is positive. So the right side of 3/2 will be positive. What we now know is that we are increasing from 3/2 to infinity. We are decreasing from negative infinity to 3/2. Because we stayed decreasing at the critical value of 0, that critical value is an HPI. And if you put 0 into the original equation, you will get 0. When you look at 3/2, we go from decreasing to increasing, so 3/2 is a relative min. And if you put 3/2 into the original equation, you get the lovely number of negative 27 over 16 for the y value. There is no relative max because we have nowhere where we went from increasing to decreasing. Now we need to find concavity. So we're going to find our second derivative. The second derivative for this function will be 12x squared minus 12x. Set that equal to 0, and notice that we can pull out a 12 and an x. Pulling that out of both terms will leave us with x minus 1. So our possible inflection points will be x equals 0 from the 12x, and will be x equals 1 from the quantity. Put those numbers on the number line. And now we are going to test in the second derivative. To the left of 0, let's do negative 1. If I put negative 1 into the factored form of the second derivative, I will have negative 12 times negative 2, which is positive. So to the left of 0, we will be concave up, positive. Between 0 and 1, there isn't a wonderful number because everything between 0 and 1 is a fraction. So the easiest fraction to test would be 1/2. If we put 1/2 into that derivative, we would get 6 on the outside, and 1/2 minus 1 is negative 1/2 on the inside, and that would give us a negative answer. So the area between 0 and 1 is negative, which will be concave down. Then do something to the right of 1. Let's do 2. Put 2 into that derivative. You will have 24 times 1, which is positive. So everything to the right of 1 is positive. So we now know we are concave up from negative infinity to 0, and again from 1 to infinity. We are concave down between 0 and 1, and because we did change signs on each side of the numbers, both of them are inflection points. So we have inflection points at 0, put 0 into the original, you get 0, and at 1, putting that into the original, you get negative 1 for your y value. I have summarized all of our information on this screen so that we can now sketch our graph. Remember that maxes, mins, HPIs are points on the graph, and inflection points are points on the graph. So start out by graphing those points. The relative min at 3/2 or 1.5 and negative 27 over 16 is not quite to negative 2. So we're at 1.5, not quite to negative 2. We have no max. We have an HPI at 0, 0. And then the other point that we have is at 1, negative 1, the other inflection point we have. Now let's look at the increasing and decreasing. What's happening with the negative infinity? Let's look for that first. Negative infinity is where we are decreasing. We are decreasing all the way from negative infinity to the 1.5. So we're going to be going downward, but notice that we're staying concave up till we get to 0. Then we are concave down between 0 and 1, so we need to make a little bit of a cup between 0 and 1, then we start going concave up again, and then at 3/2 we start increasing. So there is a sketch of the graph of this function.